Welcome to another data science deep dive on our technical track. In the following presentation, Nicole Hu, CTO at One Concern, goes in depth about using AI to create impactful solutions. She details the importance of approaching problems with an open mind, using technology or combination of technologies that is the most effective for solving a particular problem. She talks about how in the era filled of countless AI and machine learning solutions, AI is not always the answer.
Thank you, everybody, for having me here. So many industries are being transformed by using technologies that are typically not traditionally used. And these non-traditional technologies can really be used as a force multiplier for critical decision making. So for today, I'll be focusing on a few specific non-traditional techniques like leveraging automation and the cloud, using machine learning techniques, and exploring network analysis models and how these techniques are leveraged at One Concern to provide a more holistic picture of disaster risk, hereby enabling enhanced resilience. I'll give a quick background about One Concern. So we couple artificial intelligence techniques with existing physical disaster models to predict risk due to disasters. And we help leaders identify key vulnerabilities and make data-driven decisions. Ultimately, we are working towards quantifying resilience from catastrophic perils so that one could measure your risk, mitigate your risk, or transfer your risk as well. At One Concern, we don't believe AI is a one-stop solution. In fact, we believe that it's always about solving the problem and that we must focus on solving the problem. Several times, the problem is so complex and the ecosystem that you're trying to address is also so complex that multiple different techniques really do need to come together. Many times there are multiple companies who fail because they want to invest in technology for technology's sake and are just looking to figure out how they could insert AI into like multiple problems, versus looking at what the problem itself is at hand. And we believe that disaster science and resilience is one such area wherein we really do need a combination of multiple different techniques to solve the problem, and that we really do need to couple AI with with the non-traditional techniques I mentioned, to like cloud and network analysis. So I'll dive deeper into the techniques I mentioned. But before that, I want to give you all a brief, naive background about what are physical hazard models or disaster models. When we build physical hazard models, typically they use a very few features. And what they're looking at is how these few features are contribute towards impact or risk. And they try to understand what the relationship between these features could look like. These could be statistical models. These could be actually running physical equations as well. An example would be what they do is they try to understand how does the building age of a building correlate to the strength of a building during an earthquake, or even like based on what we understand of elevation, how would maybe water flow during a flood? These are type of questions which these hazard models try to solve. There are actually a lot of hardcore scientists out there, running a lot of statistical experiments to understand these features, to continue calibrating these features, and to understand like how these features correlate, what's the correlation or causation from these features as well. There's also a lot of research in even trying to understand that, hey, can we think outside the box and look at other features, how other features might be contributing to disaster risk. And that's all fantastic. We should all encourage more investment of this hardcore research because it only just scratches the surface. And investment in that research ultimately helps us understand what features would contribute towards disaster damage. But now, because of the complexity of these physical hazard models, what ends up happening is that it takes a relatively long time to calibrate these models to a particular location. Scientists take a long time to even figure out exactly how does building age maybe contribute to building strength. They would actually sometimes even build the building model itself and give it a lot of shaking to even understand like how they should calibrate certain physical equations. So that's a long time, and so that's one limitation. And another limitation is also surrounding how proper experimentation for validating these features, ease of calibration is hard, and ability to add definitely new features to the model is very, very hard because these are actual physical equations. So therein comes the the advantage of machine learning, and we augment the best of physical hazard modeling with machine learning techniques. And we are trying to solve two hard problems. We believe machine learning solves two very key problems in this space. Number one is that complete data sets are very, very hard to obtain. There are a lot of gaps in your data sets. Sometimes the data sets are non-existent. And sometimes you might have some data columns filled in one location, but not filled in a different location. And that makes it very, very hard to actually plug that into a physics-based model. The second one was the one which I talked a little bit about, which was the models itself are so complex. And so what ends up happening is that these models are not built to inherently learn from previous historical events. If you want to use them, there's a long process for careful tuning and careful calibration. Occasionally, the calibration is also manually tuned. And that's another area where we think machine learning can solve as well. So how do we do this? To solve the first problem, many times what ends up happening is people do not proceed with creating a model just because the data is not present. But we believe that the value of data augmentation and data synthesis, ultimately leading to ability to even predict impact, is much larger. So we believe in using machine learning to even solve the data challenge. I'll talk a little bit about one of the projects we did for a seismic model. Now, if we want to predict whether a building would be impacted, first you would obviously need to obtain the right building data. So we wanted to predict what the impact would be to soft story buildings in San Jose, California, but there was no data set for where these soft story buildings lie. Now, a soft story building is typically a building which has a garage at the bottom. And so what ends up happening is the foundation is weak, and they're generally weaker than average when an earthquake strikes. So instead of stopping and deciding that, hey, we cannot build an earthquake impact model, we looked at how we could even figure out which buildings are soft story buildings. We initially, we looked at what data sets are out there. We had data sets for San Francisco and Mountain View. They told us which buildings were soft story buildings. And we had other building features like building age, building height, building location, and multiple other features. So we built a bare bones machine learning model initially to just find a subset of potential soft story buildings in San Jose. Once we created that initial model, we then also ended up building a deep learning model which used computer vision on Google Street View to further narrow down the number of soft story buildings. And then we did a third set of exercise where we did spot checking, wherein we would go to this subset of buildings and see which one of those are actually soft story and which were not. And that ultimately also fed into the first machine learning model as well as the deep learning model. This is something we presented at the Southern California Earthquake Center, and this is one small example of how we even work towards augmenting the underlying data set itself. Now, like I said, the second way in which we use machine learning is in auto calibration and in making sure that models can learn from each event and they are calibrated closer to reality. Whenever a new event occurs, it is much more easier to test and auto calibrate, our machine learning models so that these models work better for the next disaster. And like I said, traditional models are very hard in tuning, so they struggle in keeping up. So even figuring out how we could easily do auto calibration or sometimes completely replace it with a machine learning model is very, very advantageous. And in the era of climate change, wherein you're seeing impacts like never before, it is even more crucial that you're able to collect information of how buildings or people have been impacted so that your models can quickly learn and so that it can adjust to and better predict for the next disaster. Now, like I said, it's not about modeling alone. And when we started deploying models, we realized that there were another hard challenge we had to solve. And that was actually on how we would automate and how we would use cloud to actually deploy these within cities. We had to figure out how we could do it on demand, how we could do it on scale, how could it be cost efficient. We had to figure out how we don't create manual pipelines, but instead focus on automation for all the different data pipelines out there. The traditional hazard models, when they're built, they can be compute intensive. And even the way when they build, they usually rely on fixed or static data sets. And those data sets are occasionally hard to secure. But if we are trying to use these data sets in a live setting, we want to make sure we can automate and actually get dynamic data sets into one location. And not just that, because we are working on a response setting, we want to make sure that the model is complete in time, so we can create a map or an impact map which is actually useful to somebody on the ground. Organizations who have typically automated the space and are using pure hazard models, they generally have access to supercomputers, and they are not necessarily focused on optimizing those models to run quicker. But we definitely had to, and that was because we do leverage both hazard models and machine learning models in our stack so that we can provide that impact to cities. So, so that's a big piece of how we use the cloud. It makes it easier for us to just have a unified single place to collate all these different types of data sets, whether be it dynamic or be it static, and we can also decide to pull in these data sets on demand. So whenever we actually want to. So when we know that a disaster is happening, or when we see a trigger happening, only then we can start triggering few models or pulling in data sets, so that way we are also being cost efficient, and also we can quickly scale and add more cities. The third technology I alluded to was a network analysis. So I'll talk a little bit about how we use network analysis to augment physical hazard modeling. When we look at traditional hazard modeling, it is focused on direct impacts. And what I mean by direct impacts is these models predict what is the damage to one building, the direct damage to one building. But again, like I said, it's about solving the problem. And the problem which people ask is not whether my building is damaged. The problem people generally ask is, when will my business recover? Or when will my city recover after a particular disaster? We also noticed that if we sum up the time to repair buildings in a city, it does not equal the time taken for the city or the organization to recover. And that is because of these indirect impacts. I'll give you a good example. A hospital might be completely structurally sound after an earthquake or a flood, but if it loses access to power or loses access to water, it is still not functional. And so how do we actually solve that problem? So we use a multiple of we model impacts to networks. We look at indirect impacts to power, water, roads, and bridges, and we use that to solve and provide the right problem to our customers as well. I'll go through a few use cases of how we are using machine learning or cloud and automation or network analysis, and coupling those with physical models in the next part of my session. On the screen right now, you're looking at a map of an earthquake damage map in Seattle. Basically, you can see that we're doing block by block level damage. A dark red means high likelihood of collapse. A lighter color means a low likelihood of collapse. And if we went through a pure physical based model, it'll take a lot of time to actually do it building by building and block by block, because we have to model all the blocks or all the beams of every building, and then look at how the shaking looked like. It's a fairly complex problem. We wouldn't be actually able to provide a map pretty quick after disaster. So in the simplest form, what we instead did is what you're seeing on this screen right now. On the left-hand side is actually widely accepted current state of the art. So we're looking at data sets like, earthquake intensity, and how do people actually interpolate earthquake intensity between buildings. We're looking at data sets like, building characteristics, structural type, year built, and height. And then you also collect soil characteristics. In the middle is actually the physics-based model, but instead of running a physics-based model, we collect a few features, and this is called fragility function. And that actually becomes featured into a machine learning model. And now on the right-hand side is wherein we are actually building a machine learning damage model using what is already known of seismic science on the left-hand side. What ends up happening is we are creating this damage model also by looking at data from historical events and earthquakes, so that we, like I said, we could auto-calibrate more easily as we see more actual damage on the ground, or if we see any more new earthquakes. I'll go quickly through validation of our machine learning seismic model. This is a map of the expected sum of predictions for a US model. blue is the sum truth, green is a pure physics-based model, and red is our machine learning seismic model, wherein we're using the physics-based features as input into a machine learning model. And you'll notice that our machine learning model is closer to the truth. So machine learning model is more closer to the truth. Sorry about that. And you'll also notice that the physics-based model is more conservative, which is natural, which is typically how these models are created. This picture is only on the 20% test set for across all the damage we have for US earthquakes. Another type, we do multiple other machine learning metrics, but one of them I wanted to talk about for validation was spatial validation. Given that disaster science, basically you are trying to understand how that one location behaves, and there are multiple facts like soil and earthquake fault. It's important to see whether your model is actually performing spatially right. On the left-hand side is seeing a basic visualization of how the Napa earthquake looks like, and on the right-hand side, we are looking at what our model predicts, and you'll notice that this is not obviously 100% accurate, but you can at least still see that we pick out the main neighborhood areas in different locations, and we're able to provide that to cities and corporations immediately. We're also deployed to a city in Kumamoto city in Japan called Kumamoto City, and you'll also notice similarly here we're able to capture the broad neighborhoods wherein damage would take place. This is something we deployed, and we always are still continuously evolving and improving our seismic model. Now, apart from how we do the modeling itself, and like I said, we also do we use machine learning for data synthesis in the input data. But a unique feature about earthquakes is that there's actually a big lack of the output data, which is damage data. We don't see a lot of earthquakes, and so very easily a machine learning model might find it very hard to predict impact. And that is another example wherein we also use a physics-based model to supplement. So you see this picture here. This is a sample image of all the output data we have for damage across multiple different types of buildings and multiple different types of soil. And you can see that there are gaps in some places wherein the entire segment is empty, or there are gaps in some places where for particular buildings, the segment is empty. So what we could do here is we could use typical statistical techniques to fill it up, but what we interestingly also do is we actually run the physics-based model, we see the output of the physics-based model, and then we fill in these boxes with how the physics-based model would actually predict impact during disaster. And so in this way, even the output damage gaps are still supplemented by the physics model itself. Another way in which this diagram is useful is that it helps us understand where our gaps are. So whenever there is an earthquake, we could try to focus collecting information on only these particular gaps. Historically, we have collected data from real earthquakes. We've been to an earthquake in Indonesia, in Mexico, in Alaska, etc., and those data sets immediately get supplemented into the history of earthquakes that we have as well. Another way we use the physics-based model is also during validation. So when we're creating the machine learning model for seismic, we want to make sure that it is actually still satisfying, actual ground truth of how a seismic model would perform. And so we run a lot of trend plots to see like, hey, how would like with increasing shaking, should your damage increase? Or with the increasing softness of soil, would your damage change or not? And so we do these plots, which you're seeing on the map. You notice that they're not completely smooth and there's some jaggedness. And that's because we're using a machine learning model instead of a physics-based model. A physics-based model would actually give you that smooth curve. But you also notice that it is all going in the right direction. And that helps us understand that the machine learning model is inherently learning how seismic science, a typical seismic science model would predict impact. At one time, we had a model wherein the machine learning metrics, which you saw before, were doing well. but the trend plots were not doing well. You were seeing like a lot of jaggedness in the trend plots. Versus we had another model wherein the trend plots were much smoother, and the machine learning, the actual validation metrics were a little bit lower. And so we decided to go with the model which had smoother trend plots, and smooth and the slightly lower validation metric, thereby showing that we want to make sure that we're not completely disregarding physics of the model as well. So this was an example of how we couple the best of physical models as well as AI. For seismic alone, we have like a pure machine learning model, but we are using the physics model to not just be as features into our machine learning model, to also help us understand how we should validate better, and to also fill in gaps in our output data as well. That'll go into another model we use, and this is a flood model. Flood model. The map here is actually a map of how which Kumamoto city to use right now. The hexes show the amount of inundation or flooding. At the bottom, you are seeing a timeline of flooding, so we are forecasting into the future. And on the left-hand side, you're seeing what is the level of water at a particular point. Now, in this model, we actually found it more hard to completely replace it with a machine learning model. So we actually really do couple physical models which are running on the ground along with the different AI techniques. So let me go through that pretty quickly. On the top level, you're seeing our data level. So we're collecting weather data as soon as we get any new weather data that's being collected. In the middle, we have the natural environment data. So this is data like elevation, or river bed bathymetry, which is basically the shape of the river. And on the right-hand side, we have built environment data. So this is like what buildings are present, how tall are the buildings, etc. In the middle layer, we have the physical models themselves. Each of these models predicting a particular type of flooding, riverine flooding, coastal flooding, and urban flooding. And on the bottom end, we have another physical model, which is actually integrating the outputs of a middle model to give one prediction of inundation, what the inundation level would be in a particular city. And how we infuse AI and machine learning across these different ways, I'll talk about it a little bit. On the top part, like I have talked about multiple times, we focus a lot on data imputation, and we use different techniques to do that. In one river canal in Kumamoto City, we actually didn't have the shape of the river bed, so we use an unsupervised learning model to fill it up. And we then actually even had one of our employees canoe through the river to get a few points and sort of see how well we are performing. So that's an example of where we did data imputation. Please note that we also do validation on the entire system. So then that's another way we also check whether or not the data imputation was right. And then for the models themselves, some of these models have very important initialization parameters, and they're very, very hard to calibrate. So we have a lot of river gauges as well as coastal gauges, which are actually looking at the water level or the water flow at different points in the city. And so before we deploy to a city, we make sure that our models are conforming to actual observed ground truth. And then even during the event, we collect the current river gauge reading and auto input that into a model so that the future forecast would be more accurate. So that's a way in which we are also auto calibrating, calibrating initial parameters, and also auto calibrating our output using machine learning techniques. I'll quickly go through the validation metrics. Ignore that we previously had a different inundation model called DELF. We recently moved to a new inundation model called MOI. But you'll see that we have, it's improved from previously a 20% bias to negative 20% to a 10% bias. And we have a RMSE of around 0.48 centimeters right now. This is the model we're actually going to be deploying soon in the next month. And 0.48 basically means there's 48 centimeters of difference between what we predicted and what the claims data told us. And that was a reasonable threshold for us to go ahead with this model. In Kumamoto City, particularly, we didn't have actual flood inundation extents. We only had claims data, and we need to know that the claims data also have some uncertainty because we don't know how true they were, etc. So a combination of the fact that a 48 centimeter difference is fine, as well as the fact that there is uncertainty in the claim data, prove that we can still go ahead, with our Lisford Moe model. I also want to quickly go through how our model performed in Hurricane Harvey, which was a hurricane in Texas. We ran the same Moe model, which we're deploying in Harvey, and there we actually had observed flood extent thanks to USGS. And here we were able to have better metrics, not just like the claims metrics, but metrics from a spatial perspective. And our hit rate was around like 97.5, and a threat score was around 82.3. And this is something we are constantly also working on. With that, so this is an example of how we are taking physical models and coupling them and using the best of machine learning or AI techniques to actually predict flood impact on the ground. The third part, which I was talking about, was network analysis. I'll go very quickly over this as well. On the left-hand side, you're seeing what the actual power network damage was in a Nisqually earthquake in Seattle in 2001. Right-hand side is what we are predicting. This is something which is still internally developing, and that's why you're not seeing product snapshots. But how we actually do this is fairly complex. Number one, we obviously predict the damage of a building because of that particular earthquake. But then we also are trying to predict what would the power network look like. So, and then we also try to predict, once we have the power network, which building derives power from which sort of subsystem. And all of that is predicted and synthesized. And then we again have the power network go through our seismic impact model to ultimately predict power damage to that power network, and then correlate that finally to power loss at a particular building. So there's multiple different steps there. And we assume that we have almost no power data except for those which are openly available. And so we believe we're still doing pretty well. We actually did have the real data from Seattle because they are our partner. But if we had to deploy this to another city, is an example of maybe potentially how it would look like. So this is something we are working in collaboration with Dr. Seth Fukima's group at University of Michigan. We did something similar for Kumamoto City. In the previous one, you looked at damage to the power network, but here we're predicting whether the building itself will lose power or not. This is, like I said, still in research. You'll notice that we're actually using Kepler to visualize our solution here instead of our actual product. Now, after all of this, I want to talk about some of the challenges we still have while building these systems. The first challenge we have is about making sure that we get the right business objectives. Many times, the data owner might be different than the ultimate business owner. And if they are not aligned, we're not able to actually solve the problem. In fact, many times that is the biggest problem versus the modeling itself. And then you also want to make sure that you understand what use case you are trying to solve, because your use case can also change the way your model KPI should be built. I'll give you an example. If we were building a seismic impact tool for just the emergency manager, they may say that in the first 48 hours, they want the highly damaged buildings to be the most accurate. In the next 48 hours, they want every building to be relatively accurate. So and that is because in the first 48 hours, they're focusing on response, and the second 48 hours, they're focusing on recovery. Similarly, if you were selling the model to now an insurance claims expert, they might say that, we have complete certainty on the completely damaged buildings and the completely safe buildings, but we need to efficiently send our claims officers to the ones wherein we have a lot of uncertainty. So give us a model which tells us the middle ground, like what the middle ground would look like, so we can focus our efforts. And so you notice that even the use case that I'm bringing up is very different. And so the KPIs you would build for your model also can be very different. And so making sure that that is clearly understood and part of your model process is something which is a challenge and something which we try to make sure becomes better over time. A way by which we solve the challenge is through diversity. So we have a lot of different diverse team members within the company. We have AI experts, engineering experts, hazard experts, and we also have a lot of industry experts in insurance and in emergency management, so that we can understand what the actual problem is and we can try to tackle these problems in different angles. Why is this a challenge still for us? It's because we don't know how we would scale this. It is something we're actively learning to figure out, especially also in the COVID situation. How do we make sure we have an effective, diverse team which also scales? And so, but this is a big strength of what we do and helps us solve the challenge in number one. The third part is on data scarcity. I've brought it multiple times. We strongly believe that you shouldn't have all the data sets before you build a probabilistic model. Even the data set themselves could be augmented and could be inherently probabilistic to still create, final impact model. And that shouldn't stop the fact that you're trying to solve the problem in the first place. But with this, when we try to solve, and there are multiple ways in which we're trying to solve that. But with the data scarcity issue, what then becomes the eventual outcome is that risk communication becomes very clear, important. You want to make sure you are erring on the side of oversharing and being very transparent in how you're collecting the data, how you are actually creating these models, how should customers actually use your products in supporting the decision making. And remember, like I talked about, like we have industry experts as well. They also help us understand not just how a model should be created, but also how should people on the ground be using our product. And because this is new, we want to make sure that there is a human in the loop through every process we do while we're delivering a product. The final issue is this is something we didn't realize would be a problem initially, but over time, as we are collecting all these different data sets, we realize that data security is very important, data privacy is very important, and at OneConcern, we are working towards multiple ways in ensuring that we maintain the secure end-to-end data governance as well. So finally, as a conclusion, we as OneConcern, we are looking at using machine learning and non-traditional techniques to transform industries transform different industries and see like how these techniques could be used as a force multiplier to actually to make decision making much easier for these industries. We have a few challenges, just like anyone else in the AI space might have, and we're tackling them in multiple different ways. Sometimes we tackle them through the ways we talked about, which is by using cloud or using network analysis. But all these different non-traditional techniques, when they come together, that is when only then are we able to provide a clear, holistic picture of external risk. And finally, a very key point as well is making sure that you do have human insight as you're developing these models, and they are part and parcel of your process. Human insight in the form of disaster experts who understand what, or physical model experts who understand what your model should be doing, as well as human insight instead of people on the ground who understand how your models could be interpreted. Hiring these experts in-house or having partners is very, very key as well. And I hope what I discussed today will encourage you all to continue doing the great things that you do, and hopefully also continue transforming industries if that's an area you're focusing on. Thank you, everybody.
That was a presentation by Nicole Hu, CTO at OneConcern Inc., who spoke about using AI to create impactful solutions and to approach problems with an open mind when finding the most effective solution for solving particular problems. If you'd like to watch more videos like this, you can subscribe to DSS Insider, link in the comments section, and please follow us on here as well by subscribing to our channel below. Thank you.